Hello guys, welcome back to my YouTube channel. Today I'm going to be talking about carbocation rearrangement. So there's going to be two types of carbocation rearrangement. One will be the hydride shift. And as indicated in the name, this is when a hydrogen, indicated in pink, that lies on, in most cases, a 3' carbon, so a carbon that's attached to 3 other carbon-based groups, and is 1 carbon away from a 2' carbon, or it could be a 1' carbon, that has a positive charge, hence is cationic. And it takes its 2 electrons, because there's 2 electrons in every bond, because, well, what's a bond made up of? It's the sharing of 2 electrons between 2 atoms, where each atom contributes 1. The hydrogen takes the 2 electrons in that bond and it jumps and it attacks that carbocation. So what happens, this carbon would have 1 hydrogen, is the pink one jumps to the 2' carbocation, and then it leaves the one that was initially 3' in a deficit of electrons, because this carbon lost the electron that initially was contributing in the CH bond, because the hydrogen took both of the electrons when it jumped over to the 2' carbon. Then we get the change from a 2' carbocation to a 3' carbocation in this example. And 3' carbocations are much more stable than 2'. Now the reason this is because if you have a 1' carbocation, it would look like this. This is a 2', this is a 3'. A way you could look at this is, if you are cationic, you are in a deficit of electrons. That means you want electrons at all moments. You're really sad. You're like, please give me electrons. But if you're a carbon group and you're attached to other carbon groups, these groups are very electron rich. So CH3 groups are very electron rich, but they are generous. They're not like a bromine or a fluorine that are electron negative, which are thieves of electrons that want to take electrons from you, which would make you even more sad and more cationic. They will actually give you electrons. They're like little electron throwers. So here, if you're attached to 2 CH3 groups, that means you're getting more electrons. And if you're attached to 3 CH3 groups, you're getting even more electrons thrown at you. Hence, you're not as cationic. You're more like neutral. Therefore, you're the happiest. So increasing stability with carbocations increases with the primariness. And what I mean by this is 1' is less stable than a 2', which is less stable than a 3' carbocation. And we can also have a methyl shift. So for example, when you have, once again, a 2' carbocation that is 1 carbon away from a carbon that has 4', that is 1 away from a 4' carbon. So this carbon does not have a hydrogen to donate, hence it cannot undergo a hydride shift, because this blue carbon does not have a hydrogen. So what it does instead, or the CH3 group, takes its 2 electrons and it goes bada bing, bada boom, 2 in, and it jumps. So nothing changed besides the fact that the blue CH3 group jumped to that carbon. So this carbon, the one that was initially green, gained a bond. Well, it also gained an electron because the CH3 group took that green electron with it. So that left the carbon in a deficit of electrons, so cationic. Well, what this did was it moved a 2' carbocation to a 3' carbocation, which is way more happy. Let's do another example. So let's say we have the following structure. Would a hydride shift or a methyl shift occur? Which one? So what do we have? You have a 2' carbocation. So now I'm going to look to the left and to the right. Here, I also have a 2' carbon. So that's not going to help. But here, I have a 3' carbon. So it has a hydrogen that can jump 1 carbon away, 2 in, which will leave the 3' carbon in the deficit, because the hydrogen will go to the initial 2' carbocation. Therefore, the carbocation, which was initially on a 2', is now a 3', where 3' is happier and more stable because it has more donating groups helping it as it's in that deficit state. Also have the case where we have a 2' carbocation that once again is 1 carbon away from a 3' carbon. And the hydride can do the same thing. It can do the jump. Therefore, the positive charge will change to that 3' carbon, and it is now a 3' carbocation. But now look, it's actually even more stable than the last example because of resonance. So these 2 electrons can go 2 in. If I count my carbons, carbon 1, 2, 3. The carbon at the end of this chain will now bear the positive charge. And the carbon with the initial positive charge will now be neutral. So label my carbons again, 1, 2, 3. These 2 electrons moved from 1 and 2 to in between 2 and 3. So the pi bond jump. And then carbon number 1 will now have a positive charge. So now this positive charge is distributed between 2 different carbons. This would be like if you had to carry in 6 bags of groceries into your house. But then your friend came along and was like, hey, I'm going to help you out. I'm going to carry in 2 of those bags for you. So that means you have to bear less of a load. And that'd probably put you in a better mood. It would also take you less time and you'd be happier. That's just like what these carbons feel like when they don't have to only have a positive charge on themselves. And they get to share it with another one of their friends, another carbon. Via conjugation. So let's do some questions that will look a little different, but we're doing the same thing. So will the following carbocations rearrange? Yes or no? And what kind of rearrangement will occur? Okay, starting with this guy. So what do we have? We have a carbocation that is 2'. Oh, but it has a friend 1 carbon away. That is 3'. So a hydride shift could occur. Bada bing. So this would be an H shift. Possible. Okay, well I have a 2' carbocation. So doing a hydride shift or an alkyl shift would not help me because then the carbocation would still be on a 2'. So just to draw this out, if this hydride went and shifted 2 in. Well, now the carbon that would bear a positive charge, one to the right, if that was the hydrogen that shifted. This is still 2'. Therefore, this shift did not help. No shift. Nope, nobody comes more stable. Therefore, you do not shift. What about here? We're already a 3' carbocation. Isn't that the best? Well, to my right, I have a 4' carbon. So if I did a methyl shift, 2 in, what would happen? Let's just try it out. So now the CH3 group would be on the initial carbon that was positive, and then the positive charge would be on the initial 4' carbon. And look what happens. Now this carbocation is in an allylic position, meaning that this pi bond can go 2 in, where we get a resonance structure. Now both of these carbons can share the load. Half of the time, you could say half of the time, this carbon is going to be positive, and the other half of the time, this carbon will be positive. Therefore, they are both positive less of the time. Therefore, they are both happier. The load is less for both of them. So this is better than the initial structure. So a methyl shift work will occur. All right, guys, that is all I plan on going over today. So make sure to leave a like, comment, save, and or subscribe to my channel if you like my content. Let me know down in the comments below what video you want me to do next. And have a great day.